Okay, then let's get started. Hello, everybody. Thank you so much for coming to the 20th of May installment of Paleo Perks. We have a really cool talk lined up for today. Today we'll be hearing from Thamizharasan Sakthivel, who's based at the Divecha Center for Climate Change at the Indian Institute of Science in India. And he'll be talking about sensitivity of South Asian summer monsoon rainfall to Bay of Bengal sea surface temperature during glacial interglacial periods. A bit about the format of today's seminar. We'll start out right now with a bit of welcome and announcements. Then we'll move into the talk, which should last roughly 30 minutes. After that, we'll have a moderated question and answer session. And then we'll wrap up for the day. And then please remember that during that moderated question and answer session, that you should send your questions via the chat function to the questions at Paleo Perks host, who today is Gwen. And a bit of Paleo Perks housekeeping. Paleo Perks values the participation of all folks interested in the paleo sciences. Please remember to abide by our code of conduct during today's seminar. You should be muted by default, but if you find yourself unmuted at any point during the talk, please remember to mute yourself.
It seems like Isaiah's screen might be.
Him. Yeah,
he might be frozen. That's all right. There we go. As Isaiah was saying, we're just asking that you remain muted for the duration of the seminar. There are closed captions that should be built into Zoom. They should automatically be showing up, but if not, you can go down to the bottom and click on the CC button to show them. We always invite you to nominate your peers who are outstanding early career researchers, and we'll be dropping the link in the chat shortly. And we have a weekly feedback form for demographic information, which is anonymous, optional, and encouraged, and we'll be sending that in the chat window shortly as well. And with that, I will pass it over to Thamizharasan, who got his bachelor's degree at Pondicherry University, as well as his master's, then his PhD at the Indian Institute of Science, and is now a research associate at the Divecha Center for Climate Change at the Indian Institute of Science. So with that, I'll hand it over to Thamizharasan. We're looking forward to your talk.
Yeah, thank you very much for the wonderful introduction. Let me share my screen. Yeah. Let me know if when my screen is. You can see the screen in the slideshow.
Looks good to me.
Yeah. Okay. Good day or good afternoon or good evening to everyone. Thanks for attending the talk and thanks for the Paleo Perks for inviting me. So myself, Thamizharasan, I'm a postdoc at Indian Institute of Science, Bangalore, India. So today I'll be presenting one of the chapters from my PhD thesis. So which I'll be discussing about the sensitivity, like if we change the 1 degree Celsius of sea surface temperature over the Bay of Bengal, how much it will affect the rainfall over the continent based on the evidence from the past 33 kilo years records from the Bay of Bengal. First of all, I would like to thank some of my co-authors or collaborators or the mentors, starting from Professor Proshenjit and Professor Sentinaran, who's a microplanetologist, and Professor Ravi Bhushan, who helped me in terms of radiocarbon dating, and Tobias, who was a part in terms of helping me in reconstructing the paleo temperature stratification, and Kaustubh for the constructive comments about this project, and Dr. John Kurian for helping me to get into the ship or allowing me to participate in the scientific expedition, allowing me to get the required sediment code from the required region. So first of all, a small introduction about the South Asian summer monsoon. Here I put together the ERA reanalysis of precipitation minus evaporation for past 40 years. And here you can see that this animation shows the monthly variation of precipitation minus evaporation. And here you can see that during the month of June and July, August, September, the rainfall bands moves over the South Asia. And when the month of October, November, December, reduces back and pours more rainfall over the Southeast Asia. So when we call it South Asian summer monsoon, it's the month of June, July, August, September. Okay. So there has been multiple studies about how the South Asian summer monsoon will change with the greenhouse warming. Here it's showing the few of the recent studies, and which most of the studies are showing that with increasing the greenhouse gas warming, the South Asian summer monsoon will intensify in terms of rainfall amount. And modern day, the summer monsoon contributes to 78% of annual rainfall over the South Asia. And out of this 78% rainfall, the moisture source is significantly 45 to 75% comes from the Bay of Bengal. Okay, so here I'm showing the two spatial map of rainfall. The left side one is the observational record from TRMM and the Aphrodite rainfall record, and the right one is the CFS-V2 model, which we use it for predicting the summer monsoon over the South Asian subcontinent. The major problem is that there are a dry biasness over the central India and over the foothills of central and the western Himalayas, also over the western Bay of Bengal. And this biases is due to the SST bias in this model. So the hypothetical model is that warmer the sea surface temperature over the Bay of Bengal, when I say SST means it's nothing but sea surface temperature, it leads to more atmospheric deeper convection process, which eventually increases the precipitation over the continent. This is the hypothesis which I'll be testing back in glacial interglacial time. So geological record offers a dynamic analogs across the varied mean states. Of course, we are not talking about transient states, we are talking about the mean states, providing insights into the mechanism of South Asian monsoon and its sensitivity to the sea surface temperature changes over the Bay of Bengal. So to reconstruct the past sea surface temperature, past climate, we collected the 4.3 meter sediment core and from the Bay of Bengal. I will come to the next slide showing the location. And we subsampled the whole core into 1 centimeter interval to get the high resolution. And our radiocarbon age dating suggests that our core dates back to 33 kilo years before present. So here I'm showing the left side plot is the precipitation minus evaporation during the South Asian summer monsoon, the color map. The blue means more rainfall. The orange or brownish means the more evaporation over the rainfall. And the orange diamond which you see is our sampling site, MJ17GC02. And these are the wind vectors during the South Asian summer monsoon time period. And the green one are the surface ocean circulation. And you can see that our sampling points plots in the region of no rainfall or more evaporation compared to the rainfall. And in the B panel or the right side panel, you do see the contours of vertical integrated moisture flux, along with the dotted line suggesting the Yasmos trajectories, high split backward Yasmos trajectory. And you can see that our steady site as the highest vertical integrated moisture means positive value. So positive value here implies this more moisture input, which means evaporation, and the negative values over the South Asia indicates more precipitation. So even the vertical integrated moisture flux implies that our steady area is the moisture source. And here I'm plotted the C panel, which is the blue line is a sea surface salinity over our steady area, and the pink one is the moisture flux over the steady area. So you can see that during summer monsoon, June to September, our salinity and the moisture flux are high, implying that the evaporation is high over the precipitation. And if you see the below panel, D panel, which is the Ganges Brahmaputra river runoff, and so we can see that the moisture flux over a steady area leads the river runoff over the South Asian major river, which is Ganges and Brahmaputra, which suggests that the Central West Bay of Bengal plays a major role in regulating the rainfall over the South Asian continent. So in this study, we are proposing one of the proxies, the cloud cover proxy. So over the Bay of Bengal, based on ship-based observation, it has been shown that chlorophyll A maxima depth varies based on whether it's a cloudy area or sunny area. So whenever there's a cloudy, the chlorophyll A maxima comes within the depth of 0 to 40 meters. And whenever there's a sunny, the chlorophyll A maximum depth goes to the deeper below 40 meters, which is 40 to 80 meters. And interestingly, there are two planktonic foraminiferous species which abundantly lives in these two distinct depths. One is G. bulloides, which lives in the of course it lives all over the depth, but it's highly populated into 0 to 40 meters, and Neoclobogona deuteri, which lives into 40 to 80 meters water depth. And these are the unicellular species whose texts are made up of mostly calcite, calcium carbonate. And interestingly, over the Bay of Bengal, the species abundance is proportional to the chlorophyll A concentration. It is minimally affected by temperature and the salinity over the Bay of Bengal. So making them as a proxy for the chlorophyll A depth maxima, whether the depth was in the shallower or is in the deeper part. So if there's a more cloudy, we'll get more bulloides compared to more Globigena bulloides compared to N. deuteri species. If there is a sunny, we'll get more N. deuteri species because chlorophyll A maximum that goes deeper. So we will have more productivity of N. deuteri compared to the chlorophyll A concentration, means compared to the G. bulloides. So here I'm plotted an example from two sediment trap records from the Bay of Bengal. The first panel is from the northern Bay of Bengal sediment trap. The southern panel is the near to our steady state, value steady state, in the central Bay of Bengal sediment trap. And here the x-axis is outgoing long wave radiation. Lower the value means more cloudy, which means sun is, means the solar radiation is reaching the Earth's surface very less. So lesser the value means more cloudy, higher the value means more sunny. And here the y-axis I plotted G. bulloides by N. deuteri ratio. And you can see a statistically significant correlation in both the cases, which implies that cloud cover plays a major role on this species population ratio over the Bay of Bengal. The major limitation of this proxy is that upwelling process also can shift this chlorophyll A maximum depth to the shallow depth, but interestingly, the Bay of Bengal, over the Bay of Bengal, the upwelling process is very weak because of the salinity stratification. So which discounts the role of upwelling on the shift of chlorophyll A maximum depth. The another limitation is suspended sediment also can shift the chlorophyll A maximum depth. So if you see the two examples, one is the northern Bay of Bengal sediment trap, which is near to the mouth of major river system like Ganges and Brahmaputra, and the central Bay of Bengal. The slope is shallower for the northern Bay of Bengal. It's because mostly the effect of the might be the effect of the suspended sediment. However, difference in slope, the trend is similar. So if there are more cloudy, you will have more bulloides by high bulloides by N. deuteri ratio, and vice versa. So we have used this proxy for reconstructing the cloudiness in the geological or during the past 33 kiloyears. So for reconstructing the proxy for sea surface temperature, I have chosen the species which is called Globigerinoides ruber. It lives all over the year over the Bay of Bengal. So it's making the ideal species for getting climatology mean. And it thrives in the water depth of top 20 meters over the northern Indian Ocean, so that the geochemical signature which we infer, or there is a temperature or a salinity which we will get from out of geochemical signature, is nothing but the sea surface salinity or sea surface temperature. Yes, for reconstructing temperature, I have used the clumped isothermometry. I'm not taking you more into the geochemical part. I hope I won't bore you with the geochemical part. And for salinity, we corrected for the temperature and get the oxygen isotope of seawater from the oxygen isotope of G. ruber. I'll come to the salinity part later. Yes. So there will be one question whether the oxygen isotope of G. ruber imprints South Asian summer monsoon or South Asian winter monsoon. So what I did here I plotted the A panel is the compiled surface sediment auction isotope of G Rubel. And the plus signs are the locations, and it has to be interpolated using clinging interpolation. And B panel is the forward model, which means estimated what's the expected auction isotope of this G Rubel if they precipitate from the surface water using the available information of auction isotope of seawater and the SSD data from Mira reanalysis for past 40 years. And the C panel shows the Pearson R value, and you can see that over our steady site, there's a good correlation, which suggests that the whatever geochemical signature which you get out of G Rubel imprints the information about South Asian summer monsoon time. Yes, to reconstruct the sea surface salinity or the rainfall over the South Asian summer, rainfall over the South Asia, we have chosen two sites. One is our site, the Red Diamond, and another one is the site from the northern Bay of Bengal. Conventionally, or I would say classically, the sea surface salinity reconstructed based on modern day correlation between oxygenate towards seawater and salinity, but that creates a problem over the Bay of Bengal. So here I have shown how seasonally the slope and the intercept of this relationship varies over the Bay of Bengal. And you can see that during the pre-monsoon, which is March to April, the slope was too steeper. And during summer monsoon, it is relatively shallower. And during winter monsoon, it becomes little more shallower. And we don't know how the slope and intercept was in the past. So assuming modern day slope and regression and reconstructing the paleo salinity will lead as large as 55% in the error. So I didn't use this relationship, modern day relationship to reconstruct the paleo salinity. Rather than that, I used the steady state Rayleigh model. So my model is simple. The surface seawater I have taken as a body which has one input. Over my steady area, the input is precipitation and one output, and which is the evaporation. But over the northern Bay of Bengal, the input will be two, river runoff and in situ rainfall. Okay. So if I do the mathematical or algebraic calculation, you will come up with this equation. The SSS means sea surface salinity normalized by the global ocean salinity, which is S naught, which is 34.8 PSU. And the delta 18 of seawater, oxygen isotope of seawater. And the delta 18 of precipitation is oxygen isotope of rainfall. And the beta is nothing but the ratio of precipitation by evaporation rate. And epsilon vapor by liquid is nothing but, I don't want to put a lot of confusion here. It's a temperature difference fractionation between oxygen isotope fractionation between vapor and liquid minus the kinetic, minus the wind factor, which is 5. So we have taken the river runoff input, precipitation over the Bay of Bengal and evaporation over the Bay of Bengal from the trace 21K model output. And here is the detailed flow map, or I would call it as a model thing. So over the northern Bay of Bengal, our input is precipitation and river runoff, and the output is evaporation. Over our steady state of central west Bay of Bengal, our input is mainly precipitation and the output is the evaporation. Here are my results. And the A panel orange line is the summertime solar insolation at the 30° north. And the gray line is the atmospheric CO2 record from the ice core. And the B is the clumped isotope based sea surface temperature over the central west Bay of Bengal. And you can see that during yearly Holocene, which is 8 to 11 kilo year, the average sea surface temperature is around 29 degrees Celsius. Whereas during last glacial maxima, which is 19 to 23 kilo years, 1,000 years back, the average sea surface temperature is 24 degrees Celsius, suggests that between these two main climatic periods, the SST difference is 5 degrees Celsius. See, modern day Bay of Bengal sea surface temperature mostly driven by the cloud cover. Here I have shown this modern day record from the Bay of Bengal. And as I told you earlier, that we use the G bouloides by N due to ratio to reconstruct the cloud cover. So if you see the A panel, which is G bouloides by N due to ratio with the lowest smoothen line and its 95% confidence interval. If you see back in time, along with the cloud cover, the solar or the photosynthetic active radiation available for these chlorophylls are driven by the solar insolation also. So if I subtract the trend of solar insolation, annual solar insolation at the steady site, and we come up with the anomaly record like delta G bouloides by N due to, and it matches with our sea surface salinity, at least from the last glacial maxima till late Holocene. Of course, there's some mismatch during MIS3. We are still looking into what's the reason, but we can pretty much say that from last glacial maxima till late Holocene, the sea surface temperature over steady area is controlled by the cloud cover. Whenever there's more cloudy, low sea surface temperature, whenever sunny, high sea surface temperature. Okay, so here in the C panel, I have plotted the temperature corrected oxygen isotope of seawater over a steady area, the blue points with the lowest smoothen line and the 95% confidence interval. And this orange lines are the wind proxies. So lower the detrital flux means stronger the winds, higher the detrital flux means weaker the winds. So we could see that whenever the weaker the winds, we have more localized rainfall or more rainfall over the steady site. Whenever there are strong winds, we do see the high evaporation over the steady site. And here in the D panel, I have plotted the blue points or the salinity difference between the northern Bay of Bengal, which is the mouth of Ganges and Brahmaputra, minus our steady site. And you can see that whenever the sea surface temperature increases, this B panel, you can see that there's increase in the salinity, decrease in the salinity. You can see that the salinity goes to the negative, which implies more continental river runoff, more rainfall over the South Ocean, which putting a lot of fresh water over the northern Bay of Bengal. And it matches with the pink line, which is barium by calcium ratio from the northern Bay of Bengal, which suggests the higher barium means more river runoff. So the thing or the output, which we did see that we saw the significant correlation between here the x-axis is sea surface temperature over our steady state in central Bay of Bengal, and the y-axis is the sea surface salinity difference between northern and central Bay of Bengal, which we used as a proxy for South Asian summer monsoon rainfall. We can't tell it as a mm per day or mm per month. We can tell it as an anomalous salinity difference. And we do see a significant relationship between these two parameters, suggesting every 1 degree Celsius rise in a temperature over the central West Bay of Bengal lead 0.9 plus or minus 0.1 degree Celsius drop in salinity over the northern Bay of Bengal. So the take-home message from this talk is the SSC difference between early Holocene and LGM is 5 degrees Celsius, and cloud cover emerges as a significant regulator of SST over our steady site. And the wind plays a major role of evaporation and the precipitation over our steady site. And we have come up with a sensitivity parameter that every 1 degree Celsius rise in SST over the central West Bay of Bengal increases the freshwater flux by 0.9 plus or minus 0.1 PSU over the northern Bay of Bengal. Thank you. I'm happy to take any question, suggestion, any critical comments. Yeah.
Awesome. Thank you so much for that super interesting talk. We already have some questions that have been sent to us. So just a reminder to those in the audience, if you have any questions, please feel free to send them to the questions at PaleoPerksHost. But we can go ahead and start with the first question that came in, which I will paste in the chat. Okay. This question was sent by Karthik.
Okay.
And it reads, how are the processes of evaporation different in a terrestrial environment than in a marine environment?
Interesting one. Yes. See, when I say marine environment, the evaporation mostly driven by the wind vector, wind speed, and the salinity stratification. I don't want to more complicated salinity cap over the sea surface. But if you see the terrestrial environment, it's more complicated. Also driven by the, of course, mainly driven by the vegetation, also driven by the, mainly driven by the wind vector, and also driven by the vegetation. Correct.
Great, thank you for that response. Okay, another question. This question reads, do you expect these patterns to change moving forward in light of climate change? So I will just add my own little question. In general, with your whole findings, and do you expect, your findings, or what do you hypothesize will happen moving forward?
See, right now, what we could able to show is the sensitivity in a lower CO2 condition, like 180 to 80 ppm. Like, so our CO2 range is like 180 to 280 ppm, the glacial, interglacial. So our sensitivity is in the, like in this CO2 range, what's the sensitivity? Like 1 degree Celsius rising SST. So of course, right now we are looking into the highest CO2 condition like Miocene. We have to check. So what is whether the sensitivity will be the same. Of course, there are climate model studies which shows that with increasing global warming, there will be relatively cooling over the Bay of Bengal, which will eventually decreases the freshwater flux. That's the future climate model, or I would say predictive climate models. Whereas the paleoclimate models are suggesting opposite. With the greenhouse gas like Miocene condition, you will have more high SST over the Bay of Bengal, which will eventually increase the rainfall over the continent. So there is a contradiction between paleoclimate model and the future predictive climate model. Yes, at the moment, my sensitivity is for a CO2 range of 180 to 280 ppm. The future warming, yeah. So we are currently working on Miocene record. We'll let you know.
Great, thank you so much. We have more questions coming in here. Okay. Okay, this question reads, how did you accommodate for depth of seabed, and does that affect the Beloides ratio via the presence of benthic foraminifera? And does river runoff affect the foram ratio?
Okay, so if I'm understanding correctly, how do you accommodate for depth of seabed? So, see, ours is above the lysocline. If the question is related to the dissolution of the species, I may be wrong. So ours is above the lysocline, the water depth is well above the lysocline. So during glacial, interglacial, we didn't see any dissolution effect. Does Beloides ratio affect the presence of benthic foraminifera? Unfortunately, we didn't get much benthics. We do get only 4 or 5 individuals. Yeah, that I have to see that. I don't have any answer for that. Does river runoff affect the foram ratio? Yes, river runoff affect this ratio in terms of suspended sediment, not in terms of salinity. We did check for salinity sensitivity. We didn't find any sensitivity with respect to salinity, but yes, it does affect in terms of suspended sediment, because suspended sediment decreases the photosynthetically available radiation, so which will lowers the depth of, or it will shallow the depth of chlorophyll A maximum over the Bay of Bengal. Yes, the river runoff affect this ratio via suspended sediment. Yes.
Great, thank you for that response. We actually, it looks like we have a follow-up question that we just received. So if you give me a moment. Okay, we'll Okay, I will paste it. Okay, so this is the follow-up question here. Why do you think that you found so few benthic foraminifera? Were the study sites just not deep enough to capture that population at any point in the study?
See, my basic understanding is we do get more benthic forms in the shallower side. So my steady site water depth is around 3,000 meter water depth. Yeah, at this site, we usually, based on my collection from Arabian Sea or Bay of Bengal, we usually get fewer. So I'm telling, if I take a 300 individual, in that I will get only 5 to 10 individuals of benthic, remaining of planting.
Okay, thank you. We've got more questions coming in, so here is our next question.
Same idea.
Oh, sorry, that
Uh,
was the same question we just had. Ignore that. Here is our next question. Okay, our next question. Do we have independent proxies for suspended sediment and upwelling?
So yeah, suspended sediment and upwelling. So I can use the independent for upwelling. Let me go with the upwelling first. So upwelling will be, I can use this paleo productivity proxies. It is a biogenic silica or any other productivity proxies for a suspended sediment. I'm not sure we have any independent proxy, but I'm not aware of it. It would be great if someone suggests that.
Yeah, well, yeah, thank you
Yes,
for...
people have used the G. bulloides for upwelling proxy, but it's a upwelling proxy over the Western Arabian Sea, where the upwelling was prevalent. Over the Bay of Bengal, the upwelling is relatively weak because of the salinity stratifications. So it's not driven by the upwelling over the Bay of Bengal.
Okay, thank you. Okay, we have a couple more questions that have come in. Just a reminder for if anyone in the audience has any pressing questions that they have to ask, please get those to us. Our next question reads, how do you calibrate sedimentation rate? And were there any issues with calibration in this study?
And yes, so there's no issue at all. So our sedimentation rate is based on 7 radiocarbon ages, and I assume the core top is modern age, is 1950 AD. And what I did following that is I compared the Oxen isotope stratigraphy of my core with the nearby site, including IODP site. So we do see a good temporal match, which implies there's no problem with our sedimentation rate. And this 7 are the EAMS based, oscillator mass spectrometer based ages. So our uncertainty is pretty much comparatively less compared to the beta counting or any other data.
Okay, awesome. Thank you. It looks like we are at our last question here. And this question reads, what is the halocline depth across the Bay of Bengal and how fast has that shifted spatially and temporally, and does that concern your planktonic foram data? And this was submitted by Karthik.
Yes, so halocline depth is shallower over the northern Bay of Bengal, and it's gets deeper because of less freshwater flux over the southern Bay of Bengal. Yes, it varies seasonally over the southern, but over the northern Bay of Bengal, seasonal or temporal variation is minimal because the salinity is it's stratified annually. Okay, and does it concern your foraminifera data? No, we didn't see any salinity effect or any halocline effect on our planting forms. So record. So what we did is we compared the same species abundance from the northern and central Bay of Bengal and compared with the salinity difference. We didn't see any relationship.
All right. Well, thank you so much for all of your responses and those thoughtful responses.
Thank you
to all
so
those
much for this
questions.
comments. So it's really interesting. Yeah.
Yeah. Well, it looks like unless anyone else in the audience has any last pressing questions, I think we can wrap it up here. Okay, so yeah, thank you again to our speaker. Thank you to everyone in the audience who came to the talk today. And yeah, please, just a reminder to fill out our weekly feedback form, which will be linked in the chat. Also, apologies now that I remember, I think I had some technical difficulties at the beginning of the seminar, so I hope that link was sent around. But thank you to Gwen for kind of stepping in and saving the day there. But yeah, thanks again, everyone. Just a reminder, you can join us next week on the 27th of May to hear Pam Barut talk about paleoclimate modeling. As always, if you have any questions or concerns, you can reach out to us at the PaleoPerks email. And other than that, have a great evening, great afternoon, great morning, depending on where on Earth you are. And we will see you soon. All right. Bye-bye.